This is a key to the optional review for some test prep. If you're watching it, there's some that are really similar to these on the test, so it's a good idea that you are. So first, function composition. We're going to put x plus 2 into the function f for x. So f of x plus 2 is going to be x plus 2 plus 4. So that's x plus 6. Then we take that output, x plus 6, and we put it into the g function for x. So x plus 6 has to go right here. So when we do g of x plus 6, we'll replace the x, the input, with an x plus 6. We'll square it up, subtract 2. This then needs to get FOILed. You can do that on your own. Foiling that that just changed for no reason, colors, that's weird. Will give us x squared plus 12x plus 36, and then we still have the minus 2. Distributing the 3 in gives 3x squared plus 36x plus 108 minus 2, which is going to give us 106. So there's number 1. Number 2, we're going to sketch a graph and state the domain in range of a square root function. Remember, f of x equals the square root of x is this. Square root of 0 is 0, square root of 1 is 1. It goes like this. The transformations that'll occur when we subtract 1, remember that we'll move it 1 to the right, because now a positive 1 would make that 0. And then this will move it 4 up. So we're going to have that exact same graph shouting out from 1, 4. And then 2, 5, and you might say 2, 5, why is that? Again, if you put a 2 in, subtract 1, root it, add 4, you're good to go. So there's the graph of it. The domain, we look left to right. The domain is here and it's closed. So my domain will be 4 on out to infinity. Our range, we look up and down, and our range starts here and goes up. So range, domain would be 1 to infinity. Whoopsie. I put it at 1 right here. Range would go from 4 to positive infinity. Make sure you close that at 1 and close it at 4 because that dot's closed. Inverses we didn't cover during this review week, but they were on the summer packet. So for the inverses, remember we call the function temporarily y. Makes it easier. Inverses reflect across the line y equals x. We replace or swap those out, and then we solve for y. Since y is down in the denominator, to get it off, we'll multiply both sides by y minus 4, or if you prefer to even think of middle school, you can think of setting the cross products equal. That's, legal thought. All right, and that'll equal 3. I'm trying to isolate y, so I'm going to divide by x. I get y minus 4 is equal to 3 over x, which leads y is equal to 3 over x plus 4. This is the inverse of my function that was called g. So we say g inverse of x is equal to 3 over x plus 4. The next one, equation in point slope form. Remember what that is. I like to say it's y minus the y we know is equal to the slope there times x minus the x we know. And so we've got y minus a negative 1 is equal to the slope. My line needs to run perpendicular to this one. This one has a slope of 5/6. If I steal it, I will run parallel. Parallel lines have equal slopes. I need to run perpendicular, so I need to be going downhill. And then we do the negative inverse. So that'll be the slope there times x minus the x I know. And you can just leave it in that form, and actually I'd take a point off if you didn't, because point slope form is what we leave most of our answers in this class, and it's what was requested in the directions. So don't keep going for that. Next one, some trig stuff here. So it helps to know your unit circle. Draw one if you need to, but you won't have a calculator and you won't be able to look. So if you want to go just make one singular unit circle up here to use for all of them, because I'm asking you to do, what, 6 of them here. That might be worth your time. Remember, a quick way to sketch out that unit circle is to start at the quadrangles here, which would be 1, 0, 0, 1, negative 1, 0 over here at pi, and down here at 0, negative 1. And then we can do our 45-degree hits, or pi fourths. And if you wanted to label that, remember this would be pi over 4, 2 pi over 4, 3 pi over 4. Might be helpful for you to do that even. Then we do our pi sixths. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. And you might, this is always legal to do this, but I would prefer, and then you could go label them, maybe you have a way of memorizing how to get them all on there, the whole thing, but this is what I'd recommend, because normally for the AP exam, you're not going to be asked 6 of them in a row. It'll pop up that you've done a bunch of calculus and your answer is cosine 5 pi over 4, and you really don't want to create this whole thing for a singular problem. So I'm going to go through the thought process I would suggest you use. You picture the unit circle in your head, you think about counting by fourths, and you realize that pi is 4 pi over 4. So 5 pi fourths is 1 past that, so we're right here. We know the pi over 4s are always root 2 over 2, root 2 over 2. That's what makes those nice and easy. This is in the third quadrant, so they're both negative. So cosine, which is the x value there, would be negative root 2 over 2. The tangent of pi halves would be sine over cosine right up here at 0, 1. So it'd be sine the y value over cosine. If you leave this, I will take a point or a half a point off because that's not technically a solution. We say that's undefined. If you get 0 over 1, you write 0. If you get a 0 in the denominator, you write undefined. Or in this class, a lot of times we just write D and E for does not exist. So either one of those is fine, but don't leave that. The secant of 7 pi sixths will be 1 over cosine. So I need to get the cosine. I'm going to go back over here to my circle. I need to get the cosine of 7 pi over 6. Well, if I'm counting by 6, again, it's 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. And I would, start here at 6, 6, and you're 1 past it. So in order for me to find the cosine there, I kind of need to reference over here. And right here is farther to the left, or to the right, sorry, than it is up. So it's got the bigger root 3 over 2 first. And that means down here in the third quadrant, it's to the left and down, so both of those would be negative. So secant would be 1 over cosine, or 1 over negative root 3 over 2, which you should not leave. We reciprocate that, or multiply by the reciprocal, and we get negative 2 over the square root of 3. No need to rationalize the denominator in here. It actually puts it in a worse form than it's currently in. Next up, cosecant is 1 over sine. I need to find 5 pi thirds. That's really 10 pi over 6. So if I go to 12 pi over 6 over here, look at where I'm back up here, 12 pi over 6 is 2 pi, so that would be 11 pi over 6, 10 pi over 6. It's right here that I want. So again, I'm referencing this one. You got to keep that same gap there with the x-axis. I'm going to change colors here momentarily so you can see what I'm talking about. We're looking right here. The reference angle with that same gap with the x-axis would be up here. I need to do 1 over the sine up there. The sine up there, I'm going to scroll a little bit more here so you can see it. The sine right there, erase. That is 1/2 over, and it's higher up, so root 3 over 2. And the sine is root 3 over 2. Keep in mind, though, I am down here in quadrant 4, so that sine's going to be negative. So I actually get the same answer I got for number 7. I get 1 over negative root 3 over 2, and I reciprocate that, and I can just leave it without rationalizing the denominator. Cotangent of pi is cosine over sine. Cosine is x. Sine is y. Again, I get 1 over 0, which I don't leave. I say D and E, or undefined. The sine of 4 pi over 3 would be the y value there. You just need to locate 4 pi over 3, or 4 pi thirds. So we're counting by sixths, right? We need to go 8 of the sixths. Here is 6 sixths. So 7, 8. I'm right here, reference angle over here, and that's how I like you to think it through. And then I go over here and I say, all right, that's 1/2 root 3 over 2, but I'm in the third quadrant, so my sign will be negative. So I get negative root 3 halves. And I'm done. So nice and easy. Next up, solving for x. So I want to figure out what angles between 0 and 2 pi meet this criteria. In order to attack angle x, I need to get rid of the 4. So I say cosine squared of that angle would have to equal 1/4. To undo the squaring, I need to square root. So I say cosine of x will equal. This requires a plus or minus 1/2 because both of them squared give me a positive 1/4. So I'm looking at an angle whose cosine is either positive or negative 1/2. Well, I'm going to go over here because I already drew it. So go take a look over here. Here's a cosine of 1/2. So all angles with the same gap with the x-axis going to be right here. I'm going to be down here, and I'm going to be down here. It's these radian measured angles that you need to find because they all have a cosine of either positive or negative 1/2. So again, we count by sixths, or maybe you have it memorized. I don't really care, but this was 2 pi 6 or pi thirds. This one right here is 4 pi 6. And then we go 5, and then 6, and then 7, and then 8 pi 6. And then 9, and then 10 pi 6, which is 5 pi thirds. So there's 4 answers for that one. Next, this again was on the summer packet. It was not in the big review, but vertical asymptotes occur where the denominator equals 0 and it does not cancel. So the first thing you need to do is factor the denominator. That would be 2x. And x, I'm going to need a -4 on the outside and a +1 on the inside so that it foils to create that denominator. This cancels with this. So I only have one asymptote. And if you just say -1/2, I'm going to take a point off because asymptotes are lines. So, and that's a vertical line. So it should be x equals -1/2. If you put x equals 4, you're identifying a hole in the graph. On the summer packet, I wrote that when factors cancel, they don't create asymptotes, they create holes in the graph. And we'll have a bigger discussion of that in our unit on limits. Horizontal asymptotes are actually what happens when you head to infinity because, and we're going to be talking about it in that regards later, but for example, if this is the line y equals 3 and my function goes like this, you'll notice that as x goes to infinity in this direction, the y value won't pass y equals 3. So we actually say that it's really what happens as you go to infinity. But up until now, you've only discussed analysis of powers. But as you go to infinity, this bottom's going to take way over the top, and that fraction's going to approach 0. So we say y equals 0. But you're probably used to, okay, if the coefficients are tied, if the powers are tied, I steal the coefficient. So if that had been 2, it'd be at 1/2. If it's top heavy, then there isn't a horizontal asymptote. If it's bottom heavy, the horizontal asymptote is 0. Next one up, simplifying this. To add fractions, we need common denominators, but this one's nice and easy just because they don't share a factor, just to do Chris. Plus cross, 1 times 2x minus 3 over go across or applesauce, x times 2x minus 3. Clean up the top. And you'll get 3x minus 3, which is 3 times x minus 1, over x times 2x minus 3. And that's the answer. Ironically, this was one of the most missed answers on the test. It is every year, especially for people who don't watch the video. For some reason, because I threw that down there as a cubed root, and because it's a fraction, there seems to be issues with it. So if I said what's x to the 5th over x squared, I would hope everyone in here would tell me it's x to the 3rd. It's top heavy. There are 3 more x's on top. You've been taught to subtract the exponents. Same theory over here. I reduced that fraction out front by dividing out of 4. And then I realized that on the top I have x to the 3rd, and on the bottom I have x to the 1/3. So I subtract those exponents, and 3 minus 1/3 is 2 2/3, which as a improper fraction is 8/3, and it's top heavy, so x to the 8/3 would be on the top of that fraction. That one's done. Letter C, I can't cancel across. If somebody goes like this, I'm going to like rock in a corner and cry and suck my thumb. So do not cancel across addition or subtraction. You need to factor. So on the top, 3 minus x is as good as it gets. The bottom's a difference of squares, so I factor it. And you might say nothing cancels, but I recall in the summer packet there is a couple of these where these do cancel to create a -1. They are opposites, 3 minus x and x minus 3. So they cancel to yield a -1. So the answer would be -1 over x plus 3. Next one, number 14, function composition. I've got f of x, and it tells me the function on the input triples the input and adds 1. I need to put this in. So the first thing I need to do is figure out what's f of x plus h, right? This is my input. It's going to go in right there. So I do 3 times x plus h plus 1, which is 3x plus 3h plus 1. So let's go write that over here. That's going to be 3x plus 3h plus 1. Then I need to subtract f of x itself. Well, f of x is 3x plus 1. I need to divide it by h. You might say, this is weird with all these h's. This is actually a super important what we call difference quotient. It's going to come into play when we work on derivatives in about a month. So this function composition is a particularly important one right here. So when I distribute that in, the 3x will wipe out with the minus 3x, the plus 1 will wipe out with the minus 1, and all I'll have left on the top is 3h. Cancels with the h on the bottom for an answer of 3. Next one up, number 15, graphing the piecewise function. This one we did cover in detail this past week. So I'm going to go put my invisible fence up at x equals -2. Oops, that's not so dotted. I'm going to grab a dotted line here. So at x equals, oh, it's kind of going dotted. -2, a dotted boundary line, another boundary at 1. And then I'm going to go graph these in different pieces. The first one's a line. I like to put the boundary in, and this is an equal, so I'll put a solid dot at -2. When I put that in, it'll pop a 4 out. So at -2, 1, 2, 3, 4, I put a solid dot. And to the left of that, I draw this line. Well, that line would have had a y-intercept of 3 and a slope of -1/2. It would have been sailing through right like that. So first one's done. Next one is a parabola that opens up, but it doesn't open up from 0, 0 like this one does. It opens up from -1, 0. Sorry, 1, 0. So we're going to have a parabola in between there. Now we got to be kind of careful how we draw that parabola because it's got to stop on both of those boundaries. So at -1, 0, because that's going to get pushed 1 to the left, or if you put in a -1, a 0 comes out. Then I have to see, well, what happens at the boundary, because I know I'm going to be making a parabola like this, but I can't just draw it however I want. I really do need to go plug in the -2, and when I do, I get a 1. That's going to be open, though, because of this. And then I plug in a 1, add 1 squared, and I get a 4. So at 1, 4, I will have a closed dot, again, because of this, and that's where I swoop down and hit that vertex. So you got to be very careful with those parabolas that you make sure you hit the vertex. What I get a lot of times is people put in this, and then just connect them however they want. That vertex needs to get hit. For the last one, remember these are all y equals. F of is y equals. This is the line y equals 4 to the right of 1. So I just go like this and it's done. And there's my non-continuous piecewise function. Number 16, complex fractions, fractions within fractions. We go Chris, minus is the connector, cross, all over applesauce, which would be x plus 2, times 2, and then it's all over x. So remember, those collapse down as a product. And then you need to simplify this. So you're going to go to minus x and a minus 2. The minus 2 is going to cancel with the lead 2. So we end up with a -x on the top over 2 times x plus 2 times x, and these are going to cancel. So my answer would be negative 1 over 2 times x plus 2. All right, next one up. Another complex fraction. Don't try canceling things or you're going to get 4 wrong. If you go like this right away, it's minus 4 and I won't even look at the rest of it. So don't do that. We get rid of our negative exponents. We write this as 1 over x plus 1 over y. I wish I'd given you more workspace here. Over 1 over x minus 1 over y. Nothing cancels. We have to get rid of the addition and subtraction and create a product so we can cancel. So I'm going to do Chris. For a y. Plus is the connector cross, which would be x, all over applesauce, or go across. That is all over. And then for the next one, I do Chris, which is y. Minus is the link, cross, all over applesauce. Now you can multiply by the reciprocal, but you can picture what's going to happen. These cancel off when they're on alternate levels like that. So I end up with y plus x. I'm going to write it over here. Y plus x over y minus x, and nothing cancels, and those aren't opposites. Y minus x and x minus y are opposites, but you'll notice these aren't complete opposites because that's a plus and a minus, but these are both positive. You can kind of think of it with numbers. There's no way you would tell me that those are opposites, right? So trig doesn't look like a complex fraction, but that's because cotangent needs to get rewritten. So we say cosine of theta plus cotangent is cosine over sine, all over 1 plus sine. So now I do have that complex fraction, or that fraction within a fraction. So what I do on the top is I picture that over 1, and I go Chris, cosine sine. I'm going to get rid of some of this work over here first. So I have cosine sine on that Chris, and then my link is plus cross, so plus cosine theta, all over go across, which is 1 times sine theta. Then I have the big fraction bar, and then it's all over 1 plus sine theta. Now, remember I talked about this in depth in the video for complex fractions, that when you have a like 1/2 over 3, these bottom two condense as a product. It's really this. You can think of multiplying by the reciprocal, but it's easier to just think of them collapsing as a product. So I still have the same numerator right here, all over, and then now my denominator, these two are going to collapse as a product. So it's going to be sine theta times 1 plus sine theta. Still not done, because on the top I can factor it, and factoring is always our friend. And when I take out that cosine that's in both of these terms, lo and behold, I get a sine theta plus 1. And that's all over sine theta times 1 plus sine theta. So now when I cancel, I'm left with cosine over sine for a final answer of cotangent theta. That one was fun. I like that one. All right, last up, common binomial factoring. Again, another problem that's going to be worth a lot of points. So let's take a look here at how we approach this one. We factor out anything that's in both terms. You can actually go radical with this one, and it wouldn't be too bad because of the half is just the square root. But a lot of times when they have like if this had been a negative 3/5, that is actually a worse process. So I'm going to do this one the way I taught it in the notes, and that is to pull out anything common to both. There's a 3 in both terms, and there's also x plus 2. We pull out the lowest degree of the common binomial, which is a negative 1/2. That is smaller than positive 1/2. We put down a pair of beefies, and in those beefies, we put in what we need. We've got the 3, we've got the x plus 2 to the negative 1/2, but I need that x in there. I need the link. I need a 2 to create the 6, and then I need enough to get an x plus 2 to the 1/2. Well, I'm going to need a full one, or x plus 2 to the first. Again, when you multiply, you add exponents. Negative 1/2 plus 1 is a half. Or you can think of subtracting, however that works in your brain. I clean up in the beefies and I get 2x plus 4. So when I combine that with this x, my beefies yield 3x plus 4. I have the 3 I took out, and then I have the x plus 2 to the negative 1/2, which we should really send down to the bottom as a positive exponent, or you could even put it down there as a square root. I don't care which. So that's it for that. I know on the back there's some matching of the parent functions, but you can look in your notes if you need to for that. Have a good one and good luck on that test. Over and out.